Let's take a look at another non-comparison based sort, Radix sort. So first off, what is this Radix stuff all about? So the dictionary definition of radix is, in mathematics, it's a number taken as the base of a system of numbers. Okay, so really it's about the base that's being used to do parts of this sort. Okay. So here we'll be working in base 10 numbers, which is good for us. So we'll be basically moving through the place values of numbers, so the ones place, and then the tens place, and then the hundreds place, and so on and so forth. That's great for us and great for this example, but computers don't naturally work in base 10. So typically when this is actually implemented in computers, it'll use a base that's based on a power of 2. So it could be binary base 2, but it's probably a little bit more common to use base 16 or base 256. Okay. So we'll also focus on sorting positive integers in the example here, but there are ways to work with negative numbers. In fact, this is covered in the iBooks examples. Okay, so the basic idea behind radix sort is that it does repeated bucket sorts on an individual digit place. So we'll do a bucket sort on the ones digit, and then the tens digit, and then the hundreds digits, and so on and so forth. Since we're working in base 10, we've got a total of 10 choices for digits 0 through 9. So we'll create buckets for each possible digit that we might have. So for our example, we could have up to 10 different buckets. If we were working in a different base, if we were sorting based on binary, we would just have 2 buckets. If we were working in base 16, we'd have 16 buckets, and so on and so forth. Okay, notice the order that we're going to be going through here. We'll be sorting from the least significant digit, the ones digit, first, and then we'll sort based on the tens digit. So basically we're going kind of from right to left through the digits of an integer. So this is really important. If you think about this, basically we'll finish off by sorting on the highest order digit. So an example we'll look at 3-digit numbers. So there's a ones place, a tens place, and a hundreds place. And when we're all done, we really expect the numbers to be ordered basically based on the hundreds place as the most important. So like 100 would become after 500, and so on and so forth. So the last thing we sort on is the most important criteria. It ends up being kind of the dominant factor of the final ordering. Okay, so this particular sort is basically using a bucket sort, and it relies on the fact that bucket sort is stable. So this goes hand in hand with this idea of sorting based on different digits one at a time. So if we first sort by the ones digit and then later sort by the tens digit, things with the same tens digit will end up in order by ones digits. So we'll see this in our example in just a minute. Okay, so if things are already ordered by the ones, they'll still be in order by the ones. Okay, so let's go ahead and work through our example. Okay, for my example here, I've got several numbers that I'd like to sort, like 124, 3, 12, 131, 222, and so on. So for each of these, I've indicated the hundreds digit, the tens digit, and the ones digit, just to be really clear on which digit we're sorting by. Notice also that instead of leaving digits blank, I filled in a 0. So when these are sorts of algorithms are actually implemented in a computer, of course, there isn't truly an empty spot. There's some concept of a representation of 0. Okay, so notice that my data here only includes the digits 0 through 4. So in this case, I've only need the buckets 0 through 4. So I've done this to keep this example a little bit shorter and simpler. In reality, if we're sorting integers in base 10, we need a total of 10 buckets for the digits 0 through 9. Okay, so we're going to go through the sort process. So first we'll sort by the ones digit, so the rightmost digit in each number. I'm just going to go through the list from top to bottom, and I'm going to put each list in the appropriate bucket based on its ones digit. So that goes in the 4, that has a 3, that has a 2, that has a 1, that has a 2. Notice that I'm basically appending these on in the bucket. So that has a 1, there's another 4, another 2, and another 2. Okay, now that we've got everything in the buckets, we have to collect all of the data together, and we're going to put it in order based on the bucket value from least to smallest. So I take all the things out of bucket 0, there are none. Now I'll move over to bucket 1, and we'll take the data out of bucket 1, then we'll take the data out of bucket 2, and 3, and 4. Okay, so notice after we've sorted based on the ones digit, everything is in order based purely on its ones digit, but certainly not in any particular order based on the tens or the hundreds. So we repeat the process again. We move over to our next digit over, so the tens digit. So we're going to go through our list again, placing things in buckets based on the tens digit. So 3, 0, 1, 2, 2, 3, 0, 2, and 3. Now we repeat the process again of kind of reassembling all of our values. So we'll take everything out of the zeros bucket, everything out of the ones bucket, everything out of the twos bucket, everything out of the threes bucket, and then we would get everything out of the fours bucket, which is currently empty. Okay, notice that what we've got now is we're primarily sorted based on the second digit. But when the second digits are equal, we're already sorted by the ones digit. Okay, so we repeat the process one more time. This time we're going to sort by the hundreds digit. So from top to bottom, that goes in the 1 bucket, that goes in the 0 bucket, that goes in the 0 bucket, that goes in the 2 bucket, that also goes in the 2 bucket. Oop, I'm sorry, that goes in the 0 bucket. That goes in 1, 1, 1, and 1. And now we go through our reassembly process, starting at the zeros bucket, moving each item out and over, and then the 1, and then the 2s, and then if we had any, the 3s and the 4s. Okay, so notice after this final bucket sort, everything's basically in order by the ones digit, but where the hundreds digit, but where the hundreds digits are equal, next they're ordered by the tens digit, and then finally they're ordered by the ones digit. Okay, so because each individual sort was stable, as we progressed to the next digit over, we retained the ordering of the lower ordered digits if their next digit over happened to be the same. So this really does rely on the idea of repeated stable sorts. Let's talk a little bit more formally about radix sort. So we'll look at the pseudocode, which will give us the kind of precision we need to start seriously thinking about the time complexity of radix sort. Okay, so here's one implementation of radix sort, and one of the things you'll note is that it's pretty simple and short because it relies on doing repeated stable sorts, as we already talked about in our example. So imagine that we've got a multi-digit number like 247. We could label the digits of this. We could think of the rightmost digit as being the first digit, the tens digit as being the second, and the hundreds as being the third digit. So our outer loop basically loops through these three different digits, or however many digits we have. So it'll loop through all d of the digits in our largest number, and it will do repeated stable sorts using the ith digit. So again, it would start it'd do a stable sort based on the ones digits, and then a stable sort based on the tens digits, and then a stable sort based on the hundreds digits, and so on and so forth. Okay, so it relies on a stable sort. So let's look at one potential implementation of a stable sort. So we'll do a simple sort of bucket sort. I'll talk through the code first, and then we'll start doing some basic time complexity analysis. Okay, so a couple of things about this. It is going to create an array of buckets. Then it's got some sort of a loop, and basically this loop is going through and it's putting items in the bucket. So we did that in our example as we went through the numbers. We would pick off the individual digit we were interested in, use that to select which bucket we put something into, and add it to the end of the bucket. Notice that each bucket has an append operation because it is in fact an array. Okay, so then after that, it's got this next phase. So the next phase goes through each of the individual buckets from the least significant to the most significant, and then it empties out everything in the bucket and appends it back into our existing list. So again, this is kind of the second phase of our sort that we went through. Let's start thinking about the overall complexity of this. So I'm going to kind of work through this line by line. So first off, our first line is going to create an array of buckets, and I'm assuming these are linked lists, so we can easily append to the end and remove the first item in constant time. Because we'd have to initialize this, we'd have to create each individual list, which is an object. I'm going to assume that this takes k units of time. We go through each of our k items, we initialize it to a new object. Okay, next we've got this loop that's going to iterate n times. So I'm going to go ahead and say that everything inside of this loop gets multiplied by n. And now let's break down the inner details. So there's a lot going on this one line. So first off, I'm just going to identify things that we can think of as constant time operations, and I'm going to kind of work outward. So accessing something from an array has that random access property. Accessing something we can think of as a constant time operation. So I'm going to go ahead and think of both of the array accesses as constant time. We have this part here where we're going to take an item from our array. We're going to fill it into this bucket4 function, and that will tell us which bucket it belongs in. So this is the part that would actually extract an individual digit and figure out which bucket to put it in. And the part to the right here is what will actually append the particular item to that bucket. So I'm going to assume that, at least in this example, this bucket4 thing is also constant time. Now, if we have numbers with a fixed length and n is relatively large, that's a safe assumption, but there's certainly cases where that's not true. For the time being, for a lot of real practical examples, you can consider this process to be constant time, so I'll do that here. We're also accessing B to extract a particular linked list, so I'm going to consider that to be constant time. So that entire bundle of stuff is constant time stuff. If this is a linked list and we can append to the end, that's also constant time. Okay, so that entire crazy line we can think of as a big constant time operation. So that entire loop basically boils down to order n. Okay, now let's think through the next loop, which is also a little bit complicated. So it's got this outer loop and this inner loop. The outer loop counts up to k, so it's possible it could take up to k units of time. But I'm going to kind of table that and think about what's going on in the inside loop as well. So I'm going to kind of do a little aside here. So the inside loop will look at each bucket. If the bucket isn't empty, it's going to go through and it's going to take everything from the bucket and append it, put it back into our original list, our original array. Okay, so it's only going to do this inside while loop until a bucket is empty. So it will spend k units of time looking at each individual bucket. But the stuff that takes place in here depends on the total amount of data that's stored across all of the buckets. Okay, so this stuff on the inside is actually only going to take place a total of n times. So this is kind of an unusual situation. We don't necessarily think of the outer loop as multiplying by the inner loop in this case. Or it's going to be better than that, actually. So we could think of this as either as being the better of n and k, okay? Or we could think of that, the worse of, the more time-consuming of n and k, or we could think of it as being the max of n and k. So let's think about how all this comes together. So we're definitely going to spend k units of time, and then we're going to spend n units of time, and then we're going to spend whatever is the max of n and k. So since we're already spending both k units of time and n units of time, I'm going to argue that this last piece doesn't make much sense. We've either already added in n or already added in k. So I'm going to claim that this is a total of n plus k units of time. So if we've got a lot of data, big N, that's going to dominate and really dictate how much time we've got. However, if we have relatively little data and a lot of different buckets to put data in, this process of going through and creating all those buckets and the process of just iterating through and looking at each bucket will take the dominant amount of time. Okay, so we have a little bit more complicated time complexity than we've seen in some of our previous examples. Okay, so moving on, let's go ahead and use our bucket sorts complexity to analyze our overall radix sort complexity. Okay, so let's go ahead and put all this together. So our radix sort does the repeated stable sorts. So we can kind of think of the stable sort as being done d times. And of course, we know that the stable sort, we've just identified that it takes n plus k units of time. So kind of simplifying all of this, we could say that the overall radix sort takes d times n plus d times k units of time. So depending on the relative magnitudes of d, n, and k, our radix sort could take vastly different amounts of time. Okay, so we're going to assume that big theta is d times n plus d times k. So one common example is where we have a big N, lots and lots of data, but relatively few buckets and relatively few digits compared to the number of items that we want to sort. So if we've got N that's much larger than our number of buckets and N that's much larger than our number of digits, and maybe even if we assume that the number of buckets and number of digits is constant, so maybe if we're dealing with, I don't know, 10-digit integers, we could kind of assume that they're always exactly 10 digits no matter how many of them we had. And of course, if we're working in decimal, as we've been doing, our number of buckets would also always be constant. So if k and d are both constant and relatively small in comparison to n, really the n is what dictates our overall time complexity. So we can kind of think of this as an O of n sort. Okay, so you may be wondering, why does this work? So there's an invariant here that can be useful in demonstrating why it works. So after the jth sorting pass, input is sorted by its least significant jth least significant digit. So the proof of this will be left to the next lab. So another question you might have is, when and why would you pick radix sort versus another sort? So picking the right sort is kind of a complicated topic. It depends on lots of things that can impact the performance and the overall behavior that you might be interested in. So sometimes a stable sort is preferred. So you can probably come up with some examples similar to my t-shirt example, where if items are considered the same for the purpose of sorting, we still want them to maintain their original sort. So we may prefer stable. And in fact, there are some things like radix sort that is based on doing a stable sort. So sometimes you need stable in order to satisfy other requirements. Oftentimes, in-place sorts are slightly faster than alternatives. So the radix sort isn't an in-place sort, or at least not the variation we've looked at. And some sorts just cannot possibly be done in place. So in place basically means that you're kind of shuffling things around in their original data structure, and typically not using any additional storage, or not using more than a constant amount of additional storage. Sometimes you're limited based on data type. So like if you want to sort strings, some of these types of non-comparison sorts just do not work, or at least don't work well with strings. Sometimes you might have some information about your data that can bias your choice. So if you know your data is mostly sorted, you might prefer something like an insertion sort that can be quite bad in comparison to the other sorts, but it works pretty well on mostly sorted data. You may also be biased by your data storage preferences. So if you already have data in an array, some of these types of sorts work relatively well with arrays by leveraging that random access property of arrays. But if you already have data in a linked list, you may choose some other sort that is more amenable to working with linked lists. Okay, so let's be a little bit more specific, and let's just think about how radix sort compares to some of the n log n sorts that we've looked at. So we'll do one example to get some idea of whether there's a vast difference between them or not. So we'll look at an example. We'll kind of consider this hypothetical example of sorting 1,032-bit numbers. So our n would be 1,000,000. If we think about our various sorts of fast sorts that are n log n, log base 2 of n is approximately 19.9. So 19.9 times 1,000,000 gives us roughly 20 million operations that we have to do. Okay, so again, this is kind of a simplification, but it gives us a general order of magnitude. Let's also consider sorting using radix sort. So let's imagine that we're we've got 32-bit numbers, so that would be considered 4 bytes. By the way, the idea of bits and bytes is covered in other classes like Computer Science 132. The basic idea here is that we can think of these as being more complicated digits. Instead of having just 10 buckets, we can think of having 256 buckets. And a 32-bit number is just made up of 4 8-bit parts. So each 8-bit part would kind of correspond to having 256 digits. Instead of just 0 through 9, we'd kind of have 0 through 255 for our buckets. Okay, so if we think about using a full 8 bits as our digit size, then we have a total of 4 digits. And so K is 256 buckets, and D is 4, a total of 4 8-bit digits in our 32-bit number. Okay, so then plugging in our numbers to our formula, D times N plus D times K, so that's 4 times a million plus 4 times 256, so that gives us roughly 4 million. Okay, so you can see that these two types of sorts are roughly on the same order of magnitude. It looks like the comparison sort may do a few times more work, but without further analysis, we can't really clearly say that one is better than another, although we can say that Radix sort at least looks promising and competitive. So we could try out a few other examples and show places where we think that Radix sort would clearly have the lead over a comparison-based sort.